In this video, we're talking about quadratic transformations. How can we take a quadratic and transform it? Before we get into that, I wanted to review a few things. First of all, these are on your formula sheet. Standard form is when everything's all multiplied out. Vertex form is when you have x plus or minus something squared in parentheses here. And there are reasons why we might want a quadratic, either in standard form or vertex form. It just depends on what you're trying to do. Remember, the vertex is kind of the corner of the parabola. So either the bottom of the bowl or like the top of the hill. That is the vertex. The reason we call this vertex form is because it literally tells you what the vertex is. The vertex is at HK. And you're going to see why. You maybe saw on the Desmos activity yesterday. But the vertex happens at HK. You have to be careful though, because it's minus h. So for example, let's say the vertex is at 2, 4, the point 2, 4. Then our equation would, and we'll talk about a later, but it would be something like x minus h, and so this is h, and this is k. Whatever the x coordinate of the vertex is, we call that h. Whatever the y coordinate of the vertex is, we call that k. Just so we can distinguish these from the generic x and y. Okay, so I'll do x minus h, so minus 2 squared, and then you add k on the end, 4. So my vertex is at 2, 4. Again, whatever happens in parentheses is going to kind of be the opposite. So if it's negative 2 here, positive 2 is my h. If I had negative 2, I would do minus negative 2, which would actually turn into x plus 2. So basically whatever's here is the opposite of h. K is straightforward, but this one is the opposite. For example, notice this one has a vertex at 3, 2, and so negative 3, 2 is the equation. This one has a vertex at 2, 3, and so negative 2, 3 is in the equation. This one has a vertex at 3, 1, and so its equation has a negative 3 here and a positive 1. So once again, this is the vertex. You pull this number, that's the x coordinate of your vertex. Pull this number, that's the y coordinate of your vertex. As you can see here, 3, 2. So go ahead and pause the video and try these on your own. See if you can list the vertex for each one of these. All right, so hopefully you've tried it. So this one, we've got a negative 4 here, so we want the opposite of that. Positive 4, 1 is the vertex on this one. And if you're not sure, you could graph them in Desmos and you'll see, or in a calculator. This one, we want the opposite of this, so 1/2 is our h. And then the last number always just stays as is, minus 10. So this one would have a vertex at 1/2, so half, negative 10, so like way down here. This one, for my h, I want to do the opposite of what this is. Since it's positive 6, I want negative 6 for my h. And for my k, there's nothing there. Like, what are we adding to the end of this? It can't be plus 1 because that would change it. So it's actually like plus 0. And so the y coordinate of my vertex is actually just 0. If there's nothing there, then it's 0. The function x squared doesn't have anything on the inside or anything on the outside, so its vertex is actually just at 0, 0, which we already knew that. Okay, so now that we've talked about that, I want to mention how we take parent functions and transform them. So with lines in the last unit, we started with y equals x, which is this line right here. And if I wanted to do anything to that line, I could like add 2. What happens is it takes all the outputs and adds 2, and that basically just bumps it up 2. You can see that on Desmos here. There's the line y equals x, and if I do x plus 2, it just bumps it up 2. These transformations apply to any type of function. So with lines, we would just start with an x. With quadratics, we start with x squared. That's what we call our parent function because it's the most basic function we could have for a quadratic. You should know by now that that starts at 0, 0 and goes to 1, 1 because 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. That's why it makes this U shape. So that's our parent function, but what happens if we add a 2 on the end or make it negative or put a number in front? And so that's what we're going to talk about today. Each of those things that you could do transforms this graph in some way. This is like our starting point, our return to base, but then whatever we add in is going to change this graph a bit. So yesterday you may have had a chance to look at some of these Desmos activities. That's kind of our goal for today. Oh man. Sorry, forgot about all this. Okay. So each part of this vertex form does a certain transformation. So this A value in front does actually two things. The first thing it does is it will dilate your graph, either stretch it vertically or shrink it vertically. Think about if I took your height, however many inches tall you are, and I multiplied your height by 5. That would make you way taller. Or if I multiplied your height by 1/5, that would make you super short. Same thing happens with graphs. If I take my x squared parent graph and I put a 5 in front, I multiply it by 5, that's what we call a vertical stretch. It makes it taller. It looks narrower, but it's making it taller. It stretches it. If you take your parent graph, x squared, and multiply by something like 1/5, that's going to shrink it. It's going to squash it down. And so this is an example of a vertical stretch. This is an example of a vertical shrink. And basically you use the A value, whatever's in front. If A is something bigger than 1, it's a stretch. And if A is less than 1, like a fraction here, but it does have to be greater than 0. So like a fraction or decimal. If A is between 0 and 1, it's going to be a shrink. So dilations are just a stretch or shrink. Like, you know, when you get your eyes dilated, they stretch or shrink your pupils or whatever it is. So A also does something else. What happens if A is negative? That forms a reflection, as you may have noticed on the Desmos activity. If A is negative, the graph opens down. As long as A is positive, the graph opens up. Basically, if you take x squared and you put a negative in front, it flips it over the x-axis. It's a reflection across the x-axis. You can see that on this demo here. So notice here's my A, H, and K, and currently A is 1, but if I make it bigger, see how it's vertically stretching? It's pulling it taller, and so it looks like it's getting narrow, but that's stretching when A gets bigger. When A gets less than 1, it starts shrinking vertically. And then you'll notice when A is negative, it flips upside down. So when A becomes negative, when the leading coefficient becomes negative, it flips upside down. Which makes sense. It should now be in these negative values rather than the positive values. Okay, let's put this back. So the graph opens up. When the A value is positive, the graph opens down, gets flipped upside down, when the A value is negative. I like to think of this as, look, the graph is smiling if the A value is positive, but if the A value is negative, the graph is sad. It opens down. So again, for example, if you have negative x squared, the negative just flips it across the x-axis. If you had something like negative 5x squared, this would be two things happening. The negative makes it open down, it reflects it across the x-axis. The 5 itself is going to stretch the graph, like we talked about on the last one. The 5 is a vertical stretch by a factor of 5. The negative is a reflection, it flips it upside down. All right, now let's get into h and k. H and k shift the graph. We call a shift a translation, meaning just move it in one direction or another. The k moves it up and down. So as you'll see in Desmos here, if I adjust the k value, so as it gets bigger, the graph just bumps up. And as it gets smaller, the graph goes down. And then you'll notice the h, as it gets bigger, the graph goes to the right, and the graph goes to the left, except you have to be careful because it's minus h, so it's actually kind of the opposite of that. So, the graph goes up when k is positive, and it goes down if k is negative. And then h makes it go left or right. That's because the h is right in there with the x, so it makes it move in the x direction, left or right. When h is positive, it moves to the right, and when h is negative, it moves to the left, except it's kind of going to be the flipped version of that because it's minus h. So for example, this has to do with h, I would just put that. But this one's kind of the opposite of what you would expect. For example, if I had x minus 3 squared, this is going to move in the x direction because it's right in there with the x. But rather than going left 3 as you would expect, it's going to go right 3 because this is actually a positive 3 for h. Or if I had x plus 3 squared, this would actually go left 3, even though I could kind of expect it to go right 3. These are what you would expect. So if you have like x squared plus 3, it would go up 3. And if you had x squared minus 3, it would just go down 3. This is why the vertex is at hk. Because if I shift it in the x direction by h, and if I shift it in the y direction by k, then that forms the vertex. You can see that on Desmos. If h is currently 2.1 and k is negative 3.7, then that's where the graph has shifted to. And so the new vertex, it got shifted, and so that's the new vertex. Also, there's something called an axis of symmetry. This is exactly what it sounds like. An axis is just like a line that you could reflect across. And so with a parabola, the axis of symmetry is the line that goes straight down the middle through the vertex. This is the axis of symmetry. The equation for that line is always x equals, because it's a vertical line, and so we do x equals, and then whatever your h value is, because it's going to go through the vertex. We'll talk more about that later. So again, like this one would go right 3 and up 2, and so if you go right 3 up 2, well, there's your new vertex. That's why hk is the vertex. Let's go through a few examples. This one says, describe how the graph here is different from the parent graph, x squared. Basically, we just need to go through each piece and say what it's doing. The first thing is the negative. The negative flips it upside down. So this new graph would be reflected across the x-axis. So it's reflected, you're going to have to write it in words, across the x-axis. Next is the 1/2. Those are separate pieces. The negative flips it, reflects it. The 1/2 is a dilation, either a stretch or a shrink. In this case, since it's less than 1, it's going to shrink it. Like if I took 1/2 of your height, I would shrink you down. So the 1/2 is going to be a vertical shrink. And I could say by a factor of 1/2. We want to be as specific as possible. So I want to say it's 1/2 that we're shrinking by. Next, I've got x squared. That's just part of the parent graph, so we don't need to do anything with that. Then I have a +6 here. This is going to shift the graph, translate it. It's right in there with the x, so this moves it in the x direction, either left or right. And remember, the one in parentheses does the opposite of what you would expect. Rather than going right 6, it actually goes left 6. So I'm going to say translated, or translate left 6 units, just to be specific. You could also say shift left 6 units or move left. And then it also goes down 5. So, and down 5 units. There we go. So it's reflected, shrink it, and translate. If I wanted to draw a sketch of this, I could actually do that very quickly. I know that typically x squared starts at 0, 0 and opens up, except this one got flipped upside down, so it would look like this, and then it vertically shrank, which kind of squashes it and makes it get wider. So it would be a little bit wider than usual, and it moved left 6 and down 5. So left 1, 2, 3, 4, 5, 6, down 1, 2, 3, 4, 5. So the new vertex would actually be here, and it would still be kind of wide and open down. So my new graph would look something like that. All right, this time I want to write an equation that translates the parent graph, x squared, so start here. But then we want to go left 7 units and reflect across the x-axis. Let's start with that because that's easy. To reflect it, just make it negative. So that reflects it across the x-axis. And then I want to go left 7 units. That needs to happen inside parentheses, right in there with the x, with the squared on the outside. Because it's in the x direction, it needs to be right in there with the x. And since it's left 7, I'm going to actually do +7 because remember what's in the parentheses is opposite of what you would expect. So rather than go right 7, this actually goes left 7. If you're not sure, you can test it out on Desmos and see if that really did work. So there's my equation that reflects and moves left 7. All right, we want to go ahead and try this on your own, describing how this one's different, and then there's some practice to do as well. I did want to mention these transformation rules work no matter what kind of function you have. So you guys haven't talked about cubic functions yet, but the same rules apply. If I added 1 on the end, it would shift it up 1, as long as you know what the parent graph looks like. Or if I had 2x plus 5, which is a line, and then I added 1 on the end, it would still just bump it up 1. So these same rules apply no matter what function you're working with, which is actually pretty cool.